Alright, in this video I'm working through part 5 of this 6-part question that involves recursive formulas, geometric series and mathematical induction. If you haven't already looked at videos for part 1, 2, 3 and 4, I'll provide some links so that you can check those out. Part 5 follows on directly from part 4 and it tells us to prove using mathematical induction that the closed definition found in part 4 satisfies the given recursive definition. So as you may remember from part 4, we finished up by deriving this closed format of the definition, and now we're being asked to prove that that is equivalent to this recursive version. So in effect, we're being asked to show for part 5, we want to prove that the 4fn-1 that recursive version is equivalent or equal to the 59 times 4 to the n plus 1 on 3. We want to show that that's going to be true for all the values of n. So we're going to use induction. So step 1 of induction is to show that it is true for n is equal to 1. So what we can do is we can just substitute 1 into the left-hand side and the right-hand side and see if we get the same number. So the left-hand side would be equal to 4 f of 1 minus 1 is 0 minus 1. F0, remembering, is 20, so that would be 4 times 20 minus 1. 4 times 20 is 80, so that gives us 79. The right-hand side would be 59 times 4 plus 1 on 3. And I'll need to use my calculator for this. So I'm just going to plug this into my calculator. We get 59 times 4 plus 1 is 237, divided by 3 is 79. So that's good. We can say, therefore, this is true for n is equal to 1. Now at this point, I'll turn over and we'll do step 2 of the induction, which is simply to assume that the relationship is true for n is equal to k, where k is some integer. So really what we're saying is that 4 times f of k minus 1 minus 1, that is equal to 59 times 4 to the k plus 1 on 3. We're going to assume that's true, so that we then move on to step 3 of the induction, where all the hard work usually happens, which is that we now need to show that the relationship is true for n is equal to k plus 1. Because if we can do that, then logically, following on from it being true for n is equal to 1, and if it's also true for n is equal to k and k plus 1, you can then kind of build up the conclusion that it must be true for all the integers. So how about here, I'll start with the right-hand side. I'll just substitute n is equal to k plus 1. So the right-hand side would be equal to 59 times 4 to the k plus 1 plus 1 all divided by 3. That's our right-hand side, and there's not much more we can do with that. Really what we need to do is think about, does our left-hand side simplify to this same expression when we put k plus 1 where n would be. So the left-hand side would be 4 times f of n minus 1. N here is k plus 1 minus 1, and then minus 1 on the end. So the k plus 1 minus 1 ends up as just 4 times f of k minus 1. Now, remembering that we've assumed that in step 2, f of k can be expressed as this 59 times 4 to the k plus 1 on 3. We've assumed that is true. So we can substitute that in. So we end up with 4 times 59 times 4 to the k plus 1 divided by 3. That's our f of k, and then we've got our minus 1 off at the end. So if I expand out this bracket, we end up with, we'd have 59 times 4 to the k times 4, which is essentially 59 times 4 to the k plus 1, and then 4 times 1 is 4, so plus 4, all divided by 3. Then we've got our minus 1 over the end. Now, if I get a common denominator, that's going to be 59 times 4 to the k plus 1 plus 4 minus 3 on 3, or minus 3 all divided by 3. And then doing the 4 minus 3, we end up with 59 times 4 to the k plus 1 all divided by 3, which is equal to our right hand side. So that's good. We can therefore conclude that this expression is true by induction. And as usual, depending on how you're taught, there may be a specific set of words that you may be expected to write. Here I'm just going to be the classical lazy mathematician and just say it's true by induction, but remember, if you're doing this on a high stakes exam where the marks matter, be sure to write that out in whatever version you've been taught. But that's it for part 5. So we've used mathematical induction to convince ourselves that this closed version that we worked out is in fact equivalent to the recursive version. We haven't made any mistakes or noticed an incorrect pattern. It all seems to have worked out well. So that's it for part 5. Hopefully you've followed along with all that. And in the next video, I'll finish off on this question by taking a look at part 6. All right, tick boom.